Okay, welcome to lesson 9 of module 6, linear functions. So we've been looking at scatter plots, and we have been looking at how to draw a line that would fit the data in a scatter plot. And in this lesson, we're going to go a step farther and actually write the equation of the line that we fit to data. So we're going to look at some real life data in this lesson, and so we're going to open with some data that was collected on the bite force of various crocodiles and alligators. And so they were your example says that scientists were interested in finding out how different species might adapt to finding food sources. So they were studying the correlation between the body mass of the alligator or crocodile and the bite force, so the force with which they can bite down on their prey. So I found this picture of how the bite force might be measured. So there's a type of apparatus like this. So what they're measuring this in is pounds per square inch. So how much force in pounds per square inch can the alligator or crocodile exert on its prey? So here's our data. Let's look at the table here. And so we have several different species of crocodile. The one I showed you in the opening screen is the saltwater crocodile, which is not even on here. It has the greatest bite force of any alligator. But so you can see what they're wanting to know is, how does body mass affect the bite force? And could we predict the bite force by looking at the crocodile's body mass? So it looks like this data, no, it's not in order by anything actually. But so we have body mass and bite force data for each species. So for comparison, if we look at maybe this first one, the dwarf crocodile here. The dwarf crocodile has body mass of 35 pounds. So that's like maybe a 2-year-old child might weigh about that. And its bite force is 450 pounds, and this is actually pounds per square inch as far as I can tell. But pounds per square inch, 450. So, and going up here, 45 pound crocodile with a bite force of 255. So if we come here and we look for a weight that's similar to a human, so let's look at this one, 135 pounds. Would be a small adult, small-ish adult, has a bite force of 750, 225 pounds, bite force of 400. So by comparison, a human, I was curious, so I looked it up. A human adult male has a bite force of about 150 pounds per square inch. And actually pounds per square inch I'm going to put on here because that's what we're measuring. So if you look at an adult male, would probably be around 200 pounds. So we could compare to maybe this one. The crocodile would have a bite force of about 1,000 pounds per square inch. So it's not surprising. It's more than what we have. But I was surprised that a human could have that much bite force. But that's less than even the smallest of these crocodiles. These ones that are barely the size of a child, a small child, have a bite force that's much larger than a human male. So, okay. So, another thing that's surprising is just that there's so many different species of crocodiles too, and the different sizes that they come in. So we might want to start by looking at a scatter plot of the data. So this has been done for you. It's in your notes. The scatter plot here displays the data on body mass and bite force for the crocodilian in the study. So there you have it. So it says, describe the relationship between body mass and bite force for the crocodilian shown in the scatter plot. Okay, so what is this question asking us? It's asking us to talk about the correlation, if there is any, between body mass and bite force. So I could start my sentence with something like, the greater the body mass, what? The greater the body mass, the greater the bite force. Okay? Because that's kind of what we're seeing in this trend here. We see this trend, an increasing trend, that as body mass increases this way, so does bite force. Okay? So something like that. The greater the body mass, the greater the bite force. Or as body mass increases, bite force increases also. All right. So we're also asked to draw a line to represent the trend in the data, and then talk about what you considered in drawing your line. And then based on your line, predict the bite force for a crocodilian that weighs 220 pounds. How does this prediction compare to the actual bite force of the 220-pound crocodilian in the data set? Okay, so we're going to come back over here and draw a line to fit that data. So go ahead and pause and do that now, and then using your line, predict the mass of the 220-pound. All right, so I've drawn a line that I feel like is a pretty good fit for the data. And now I'm asked to predict for the 220-pound using my line. So this is the 220-pound crocodile in our data set. Let's go back and look at where that is. 220 pounds, crocodile G, had a bite force of 1,000. Is that right? Okay, so let's go back to our graph here. Okay, so I'm going to use my line, but you're going to use yours. And I think I will actually draw a line on my graph so I can see it. So this is or no, actually that's not the 220. This one is right here. So I've drawn a line here, and now I'm going to try to bring the line over there. So mine is predicting, that kind of went up a little bit, more like maybe 900. So my line predicts, 900 pounds of force. The actual force for that crocodile was 1,000 pounds of force. So for that one, my line wasn't too far off. Yours might have been less. It could have been, anywhere down to 600 or 700. There's a wide range because we're just informally fitting these lines. And back to number 2, when you drew your line, you were supposed to talk about what you considered in drawing your line. So hopefully you have some comments there. And I would love to be in class with you, and we could compare the different lines that we drew and talk about why we put our lines where we put them. Why did I put my line right there? So But hopefully you have someone at home to talk about it with. So now we're going to look at several lines. Several students decided to draw lines to represent the trend in the data. So this is the same data, and we have 4 different lines here. And so you can see they have different slopes, they have different y-intercepts, they would have different equations, and they would predict different bite forces for the different crocodile body masses. So what we want to do is look at each of these and talk about whether we think they're a good fit. Maybe you could look at all 4 and decide which you think is the best fit. So let's look at what the question says. So for each student, indicate whether or not you think the line would be a good line to use to make predictions. And then give reasons for your thinking. So I'd like you to pause and work on that now. Really think about each graph and then come back and we'll talk about them. Okay, so as we look at these lines, remember we're trying to think, would this line be a good predictor based on the data that we have? So if we look at Saul's line, you can kind of see all these points here. For the larger crocodiles, it's going to overestimate the bite force. And for all these smaller crocodiles here, 50 to 150 pounds, it's underestimating the bite force. It's going to predict a bite force that's smaller than what they have. So this one might not be the best one. Then Patty's line looks pretty good through here. She has these that are below the line, but these kind of look like outliers too. So she looks like she has fit the line to a good bit of the data. Now, if you look at Marissa's line, hopefully you saw that she's going to overestimate the bite force for almost every bite mass. She's got all these points that lie under her line. So that means she's going to be predicting bigger numbers for bite force than what the data really shows. Okay, and let's look at Taylor's line. If you compare, Taylor's looks pretty good too, but if you compare Taylor to Patty, you can see that Patty just fit all the data better, or it looks like Taylor was trying to get close to some of these points, but for these larger alligators out here, again, he's going to underestimate their bite force. They're stronger than he's allowing for. So there's no wrong or right answers. Hopefully you just took some time to really analyze these different students' graphs. Okay, so let's go back. Let's move on. What is the equation of your line? Show the steps you used to determine your line, and then based on your equation, what is your prediction for the bite force of a crocodile weighing 200 pounds? All right, so in order to write the equation of your line, you're going to have to go back and look at it. So here's mine. So what, remember from previous lessons, in order to find the equation of the line, we're going to write it in the form. And so we need to find the slope and then put in an XY pair and solve for the y-intercept. We could kind of guess at the y-intercept, but we'll be more accurate if we actually use a point on the line to get it. Looks like this y-intercept for mine is right around, it's a little below 200, right there. But I will use a point on the line to figure it out. Okay, so Pause the video and work on finding the equation of your line. Okay, so you've had some time to work on that. So I'm going to show you my process and see if it matches yours. So I'm going to use these 2 points because my line pretty clearly goes through those points. And so these points are the point 300. I looked them back up on the data table. 300 and 1150. And this point down here is 110. 550. Okay, so those are 2 ordered pairs on a line, and from those 2 points I can get the equation of the line. So let's go ahead back to our workspace here for this problem. So here we have, we're asked to find the equation of this line. So I'm going to jot down these points again. So I have the point 300 and 1150. And I have the point 110 and 550. Okay, so this is a 300-pound crocodile or alligator has a bite force of 1,150 pounds per square inch, and then the 110-pound crocodile has a bite force of 550. Now we're asked to predict the bite force for a crocodile weighing 200 pounds. So we're going to use our equation of our line to do that. All right, so to find this equation, now that I have 2 points, I can find the slope of my line. So my slope is the difference in y, 1,150 minus 550. So that's the increase in, or decrease actually, in the y. And then divided by the difference in the x-coordinates, 300 over 110. So this is 600 over 190. 300 minus 110 is 190. And I'm going to obviously use a calculator for this. And I'm going to round it to the hundredths place. So I get 3.16 for the slope of that line. So now I know this much. I know that this equation is y is equal to 3.16x plus the y-intercept. And so now I want to solve for the y-intercept. So to do that, I can choose either of the points and put them in. So I'm going to choose the first one. So the y value is 1,150. The x value is 300, so it's times 300 plus b. And so now I'm going to solve for b. So this is 1150 is equal to, so I want to do that multiplication. And I get 948 plus b. And then if I subtract 948 from both sides, see how this algebra comes back to good use? I'm going to have that b is actually equal to 202. Okay, so where is that on my graph? So I said that it looked like the y-intercept was going to be a little less than 200, but by the points that I used here, it actually comes out just right at 200, a little bit more. So that kind of goes along with my graph. So I know I probably didn't make a mistake there. So the equation of my line now is, get a new color so I can write it. The equation of my line is y equals 3.16 x, get a better x on there, x plus 202. Okay, so now we're being asked to predict use this equation to predict the bite force of a crocodile weighing 200 pounds. So y is the bite force is equal to 3.16 times 200, put 200 in for x, plus 202. And if you punch that into your calculator, you're going to get 834. So our prediction for the 200-pound crocodile is a bite force of 834 pounds. Now, your answer could be different from this because you were supposed to base this on the equation of your line, not my line. So this is for my line, but 800 is a reasonable answer. So if you got something very different from 800, then you probably need to look at your line again, or you need to check your work on finding the equation of the line. So this is a good application of being able to find the equation of a line using just 2 points. Okay, so now let's look at exercise 6 here. Patty drew vertical line segments from 2 points to the line in her scatter plot. The first point she selected was for the dwarf crocodile. The second point she selected was for the Indian gharial crocodile. I'm not sure how to say that, but okay, so you can see that on here. Here was the actual measured bite force, and here's what her line would have predicted. And then over here, here's the actual bite force, and up here would be the value her line would have predicted. Would Patty's line have resulted in a predicted bite force that was closer to the actual bite force for the dwarf crocodile or for the Indian crocodile? What aspect of the scatter plot supports your answer? Okay, so we can see that her prediction is closer for the dwarf crocodile than for the Indian crocodile. And the aspect of the scatter plot that supports my answer is that the line is a farther distant, is further from the data point for the Indian crocodile than from the dwarf crocodile. Okay, so part B says, would it be preferable to describe the trend in a scatter plot using a line that makes the differences in the actual and predicted values large or small? Explain your answer. Okay, you can pause and think about that for a minute. Okay, so hopefully you would recognize that what we want is we want these differences here to be as small as possible for as many dots as possible on the line. So we're trying to, like we talked about in the last lesson too, we're trying to get a line that is as close as possible to all the points. It's not possible to hit them all, but we want to get as close as possible. So we want these differences here to be small. Okay, our next example in exercise 7 is about used cars. So this plot shows the age in years and the price in dollars of used Honda Civic cars that were advertised in a local newspaper. So you're asked, based on the scatter plot above, describe the relationship between the age and the price of the used cars. So pause the video and write down, what is the relationship? Okay, so the relationship that you're noticing here, hopefully, is that the older the car, the smaller the price, the lower the price. So the older the car, The older the car, the lower the price. So the price as the age increases, the price decreases. So any one of those statements would describe the trend in this graph. You don't want to just say something like it's decreasing. You want to mention when you're doing asked to write a statement like this, you want to reference both variables and talk about what is the relationship between the variables. So as age increases, price decreases. Okay, now in part B, Nora drew a line that she thought was close to many of the points and found the equation of the line. She used the points 13, 6,000, so it looks like this one here, and 7, 12,000, right there, right in there, on her line to find the equation. Explain why those points made finding the equation easy. All right, so hope you would recognize that because those points look like they're on grid lines, they're easy to recognize and write the coordinates of and to use in determining slope and then y-intercept after that. So you just need to find nice points like we talked about when we were learning about slope. Find a friendly point. She could have used any point on the line. She could have found the coordinates of a point right in there and one right up here. It's really up to you which points you use. So you just want to use points whose coordinates you can find easily. And so now we're asked to find the equation of Nora's line for predicting the price of a used car given its age. Summarize the trend described by this equation. So using the method that I used in the crocodile example, go ahead and pause the video and find the equation for Nora's line using her points. Okay, so I've rewritten the coordinates of the points that Nora picked out. And so now we're going to find the slope. So the slope is the difference in the y coordinates. So I've got 6,000 minus 12,000 and divided by the difference in the x coordinates. So I've got 13 minus 7. So this is negative 6,000 in the numerator divided by 13 minus 7, which is 6. So my slope is negative 1,000. Okay, so let's use that slope. So if y is what's on the vertical axis, so that is the what is it? It's the price. The price of the car is going to be negative 1,000 times the age of the car, which is x, plus some y-intercept right there. So I need to solve for that. So to solve for that, I'm going to put in one of the points. So let's use the 6,013. So $6,000 is equal to negative 1,000 times 13. Is that right? Yeah. Plus B. Okay, so 6,000 equals negative 13,000, multiplying that out, plus B. So if I add 13,000 to both sides, I can see that my y-intercept is 19,000. So B is equal to 19,000. So the equation of my line, let me get a new color here for contrast, is y is equal to negative 1,000 x plus 19,000. Okay, so we did expect a negative slope. If we look at our line, it clearly has a negative slope. And so what does a slope of negative 1,000 mean for this line? Okay, so it's dollars per year, right? Because I took y divided by x. So it's negative $1,000 per year. So that means every year I have my car, the value decreases by $1,000. Every year it's dropping down 1,000. So it starts at 19,000 and loses 1,000 every year. So that's what this equation right here is saying. So, yeah, so that pretty much summarized the trend described by this equation. So the car value is decreasing by $1,000 per year. Based on the line, for which car in the data set would the predicted value based on the line be farthest from the actual value, and how can you tell? So let's look back at the line in the graph. Which of these points seems furthest away? So you can pause if you'd like to. Okay, so it appears to me that this point right here is farthest from the line. The rest of them are pretty close right here, but this 10-year-old car is only, its value looks like it is, where is it? Right here, let's follow the line across. Maybe 4,000. And our prediction would be up here at, let's see, minus 10 would be at about 9,000. So that's a pretty big discrepancy there. So let's go back to our questions, and says how, okay, so which is farthest, how can you tell? So how can we say that? We could say the car valued at not the car valued at, the 10-year-old car. Let's see. The 10-year-old car is farthest from the line. And so its predicted value is going to be farthest from the actual value. Okay, so part E asks us this. It says, what does the equation predict for the cost of a 10-year-old car? How close was the prediction using the line to the actual cost of the 10-year-old car in the data set? Given the context of the data set, do you think the difference between the predicted price and actual price is large or small? Okay, so let's use our equation. Our equation was y is equal to negative 1,000 times x plus 19,000. Okay, so for a 10-year-old car, that would be y is equal to negative 10,000 plus 19,000. Okay, so to get the negative 10,000, I just multiplied 10 years, times negative 1,000. So this is the amount that the value that the car is going to lose. So the value of the car, y, is equal to 9,000, according to our line of best fit, or our prediction line. So the car should sell for 9,000, but the car actually sold for 4,000 or thereabouts. So given the context of the data set, do you think the difference is large or small? Well, I would say the difference is fairly large. 4,000 would be the cost of, let's see, where would that be? Right over here. Closer to the cost of a 14 or 15-year-old car. And my car's only 10, so the difference is large. I could say something like it's off by $5,000, roughly $5,000, which is a lot compared to the price of the car. Okay, and then part F says, is $5,000 typical of the differences between predicted prices and actual prices for the cars in this data set? Justify your answer. Okay, so we could look back at the graph and see that most of the differences are quite small. They're within maybe $1,000, or they're right on the line. So, so this is not a typical point here. So we could say no, not typical. It's not a typical difference. Most are much closer. Most data points are much closer to the predicted prices. Okay, so so let's just look at the lesson summary. A line can be used to represent the trend in a scatter plot. Often. Not always linear, but often it can. And if it is a linear trend, then we can write the equation of that line. And it says, evaluating the equation of the line for a value of the independent variable will determine a value predicted by the line. So a good line of prediction is one that goes through the middle of the points in a scatter plot and for which the points tend to fall close to the line. So we want most of the points falling close like that. Okay, so we can think of these lines as going kind of through the middle of all the points. Okay, so good luck with the problem set on that one, and we'll see you back here for lesson 10. Actually, you have that after this lesson, you can take the mid-module assessment and make sure that you understand everything in lessons 1 through 9 before moving on to lesson 10.